Hi everybody. In this video I'll talk a bit about the definitions for union and intersection, our first two operations of sets. I'll go through an example involving these, and then I'll talk through Theorem 2.22, which tells us some laws about how these operations behave and interact with each other. Along with that, I'll show an example of illustrating one of the distributive laws and talking a bit about how the other laws could be proved. Excuse me. Okay. So remember that, given two sets A and B, their union is defined to be the set of all x such that x is in A or x is in B. So an element belongs to the union of A and B if it's in at least one of A or B. And for A intersect B, an element belongs to A intersect B if x is in A and x is in B. So notice how we're defining these operations with sets by using the logical underpinnings that we developed in Chapter 1. This is going to be our window to proving some of the results in Theorem 2.22. So let's just look at an example to make sure we understand what these two definitions are saying. So C and D, C is given by 1, 2, 4, and 5, and D is 1, 3, 5. So their intersection, another way to think of intersection, it's the collection of all elements that are common to both C and D. It's a conjunction. So C intersect D, I would look at this, and I'd look at, okay, what elements are common? Well, 1 is in both of these sets, so that's in the intersection. 1's in here. Let's see, anything else common? 2's in C, but not in D, so doesn't satisfy this open sentence. 4 is in C but not D, but 5 is in both of them. So that's the other element that is in both C and D. And so that is the collection of all of them. C intersect D would just be the elements 1 and 5. For their union, C union D, I'm going to collect all the elements that are in either C or D. So everything that's in C is automatically in the union, so I'll go ahead and write those down. 1, 2, 4, and 5 are all in one or the other. But then I also want to include the elements in D. So 1, 3, and 5. Now 1 is already taken care of because it was already in C. Same with 5. That was already in C. And so I don't include those again. Remember, with a set, you don't include elements with multiplicity, is what we say. If 1 is in there, you wouldn't see 1 in there again. So what do we have to add? We also have to add 3 because that's in D. So C union D is the elements 1, 2, 3, 4, and 5 would be the union. So this is the idea of union and intersection. In Venn diagrams, we can illustrate union and intersection. So if this is my set A, so this big outside set, that's my universal set. All the elements possible are considered in the universal set. And if I have A and B, then their union, it's everything that's in either A, that would be these, or in B. So all of these. So their union A union B is all of the elements in both of those sets, like that. For the intersection, so sorry, this would be A union B. For their intersections, A intersect B has to be in both A and B. So here's A, B, has to be in A, and it has to be in B, and so we're looking right here at the intersection of A and B. Okay, so that's the idea for those. Let's look at this theorem, Theorem 2.22, which establishes some laws for these operations on sets. And remember, again, I want to stress, we have a new structure, that is sets, and new operations on those things, so union and intersection. So these laws don't just come for free, right? We have to actually establish those and prove them. Theorem 2.22 just tells us which ones are true, but we'll look at why these are true. So first off, we have commutative laws. We have commutative laws, that is A union B is the same set as B union A. So commutative law for union. We also have A intersect B is equal to B intersect A. So that's the commutative law for intersection. So I guess I'll write down all the laws first, and then we'll talk about why they're true and how you would prove them. We have associative laws for each of the operations. So again, associative means it's telling us how to associate them with each other. How does grouping work for these operations? And what it says is that if you first compute A union B, and then take a union with a third set C, that this is the same thing as first taking the union of B and C, and then taking the union with A. So that's the associative law for union. We also have an associative law for intersection. So A intersect B, and then I intersect that with C. Well, that's the same thing as doing A intersect B intersect C. So those are the associative laws. And then finally, we have these distributive laws, which are telling us how the two operations interact with each other. Distributive laws. So what is this saying? This is saying if I do A intersect B union C, well, how else can I do this? We could first do A intersect B and then take a union with A intersect C. So that's union over intersection. Should remind you of the distributive laws we saw for conjunction over disjunction. And then we also have union over intersection. A union B intersect C is the same thing as A union B intersect A union C. That those are also the same thing. So how are these established? We can prove, let's prove one of these just commutative laws. Let's prove this one. Let's prove that this is true based on the definitions or the definition of intersection. So what I want to show is that if X is in A intersect B, then X is in B intersect A, and the opposite is true as well. If X is in B intersect A, then X is in A intersect B. So that is, I want to show that X is in A intersect B if and only if X is in B intersect A. So, how do I do this? Well, I use the definitions. So, X is in A intersect B. By definition, I'll actually show an equivalence. Maybe I'll write this as equivalence is really sort of the same thing as if and only if. I'm going to show this as an equivalence, that this statement's equivalent to that statement. That's what I want to show. So X is in A intersect B. Well, by definition of X being in A intersect B, that means X is in A and X is in B. So that's just definition of intersection. That's our definition that we take. Now this, I know I can flip the order of these because we already established using truth tables that the commutative law of conjunction. So this is equivalent to X is in B and X is in A. So that's commutative law of conjunction. And now I'll build back up to sets. I'll use the definition of intersection again, but now with this statement to conclude that this is the same thing as X is in B intersect A. So that's definition again of B intersect A. And that's a proof for this. So the proof relies on the fact that we already have the commutative law of conjunction, and then just using definitions, that law, and the definitions again. And that's how we can show that these two sets are really the same thing. The statements underlying them are equivalent. So I also want to pick out one of these distributive laws. I think I want to pick out this one. And I'll illustrate why this one is true, and we'll also look at a proof for this. So first, just an illustration of why this is true. I need 3 sets. So I'm going to build a Venn diagram for my 3 sets. So here's my universe of discourse, or my universal set. and I have three sets, A, B, and C. This would be the standard way you would draw three sets so that all possible intersections are there, and then I'll just indicate by shading what is under consideration for a particular operation. So what I mean by that is I want to depict A union B, A intersect C, and then take their union, and I want to show that that's the same thing as A intersect B union C. So let's illustrate A intersect B, and then I'll illustrate A intersect C, and then I'll take their union. And then finally I'll take their union. A intersect B, union A intersect C. Okay, so let's see. So A, again, I have my three sets under consideration. I'm going to draw them like this. A intersect B, which ones are which? So I have A, B, C. So A intersect B would be just the ones that are common to both A and B. So that's this bit here, would be A intersect B, is that little sliver. I'll do the same thing over here for A intersect C. So A, B, C again. Now A intersect C would be this sliver, the set that's common to both A and C. So that's this bit. And now I will take the union of both of those. A, B, C. Taking the union of them, I want any elements that are in this sliver or this sliver. So what does that look like? That's everything in this guy and everything in this guy. And so that's A intersect B union A intersect C. That's my illustration for that. And I want to show that that's the same thing as A intersect B union C. So for this one, I'll need to look at B union C and then take the intersection with A. Okay, I'll make that a little bit bigger. C again. Forgot what I wanted to do. I want to do B union C first. So let's indicate B union C here. So B and C, everything that's in C, and everything that's in B. So that's all of this stuff. Now you'll notice there's some of this set that I just drew, some of this B union C, some of it's also in A. And so now I want to take an intersection with A intersect B union C. So I'll just take that part of B union C that's also in A. So there's A, there's B, there's C again. So there's B union C, and just this bit is also in A. So what is that? That's exactly this part of it. So notice I had two ways of doing this. One way I did A intersect B union A intersect C, and here I did A intersect B union C, and those were exactly the same sets. So these are equal. Now this illustrations can be helpful for sort of identifying why it's true. Hopefully this gives you more of an intuition of why this distributive law holds, but it doesn't really constitute a proof in and of itself. So let's actually take a proof. Let's go a little bit deeper and go down to the logic of this. So I want to show that A intersect B union C is equal to A intersect B union A intersect C. So by definition, what do I want to show here? I want to show that if X is in A intersect B union C, that this statement is equivalent to showing that, or is equivalent to X being in A intersect B union A intersect C. So I want to show this. So let's prove it. So, all right, we'll start with, how about the left-hand side, have a bunch of equivalences and eventually get to the right-hand side. Okay, so X is in A intersect B union C. What does this mean in terms of logic? This means that X is in A and X is in B union C. So this is definition of intersection. Now I can break down this B union C a little bit further. It's still in terms of sets. I can write out the definition of union. So this is equivalent to X is in A, and I need to put this in parentheses, X is in B or X is in C. And so that's just using definition of union. So I've broken down my sets into just logical statements, into an equivalent logical statement. And see how I have it broken down into X is in A, X is in B, X is in C, with conjunctions and disjunctions between them. And now, so where do we go from here? Well, how about use a distributive law? Look, I have a conjunction over a disjunction. So I can rewrite this using a distributive law. So this would be, if you need to, go back and look at that distributive law. This would be X is in A and X is in B, or X is in A and X is in C. And so that's distributive law. I'll say conjunction over disjunction. So all we did was apply a distributive law. And now I'm going to build this back up into sets. X is in A and X is in B. Well, what does this mean? This means that X is in A intersect B, right? That's the definition of intersection. And then I have or, and I can build this one back up, or X is in A intersect C. So that's, again, that's using definition of intersection, building my way back up. And now I have this disjunction between these two. So this is actually a union of these two sets. So this is equivalent to X is in, let's see, A intersect B, union A intersect C. So that's definition of union, and that's exactly what I wanted to show. So that constitutes a proof. That's why the distributive law of sets holds, because we have distributive law of conjunction over disjunction. Okay, that's it for this video. Hopefully that helped you understand a bit about why these distributive laws should hold, and how to prove them, where they come from.